seminar. Okay, so meeting is recorded. It's okay with you, right? If you do the recording, Mehmet?
Okay, yes.
Yeah. So Mehmet Doğar is an associate professor at School of Computing, University of Leeds. He is doing research in the area of robotic object manipulation, and today he's going to talk about that topic. Previously, he was a postdoctoral fellow at MIT, and he did his PhD studies at Carnegie Mellon University, graduated in 2013. So, Mehmet, welcome. Thank you for accepting our invitation. And stage is yours. Thank you.
Thank you very much. Yes, thank you for inviting me to give that talk, and it's great to see familiar faces as well, as I mentioned. So, yes, I have been at Leeds for, I arrived Leeds in September 2015, so it's a bit more than 7 years now. And I have a lab here which focuses on object manipulation. And I will talk about what we focus on and some of the recent work that we have done. As much as I had time, I won't have time to talk about everything, but there will be two halves to this talk. The first half will focus mostly on the object manipulation, physics-based object manipulation. The second part, Çağatay Hocam, you said you were also interested in the human-robot physical collaboration work that we did. So I will also talk a bit about that, but I will first start with the object manipulation focus. And particularly when it comes to object manipulation, one problem that we had been very interested in is object manipulation in clutter, physics-based object manipulation in clutter. What I mean by that, oh, it's not gonna play. It's not gonna play. Wow. Why? Okay, so let me check if my others will play. No. Okay, you can still see my slides, right? Good. So yeah, I am interested in physics-based object manipulation problems where the robot, for example, here wants to grasp this object with the green tape on it, and imagine that the robot cannot reach from the top. So it's like a reaching into a shelf or something like that. So it needs to push these objects to the side to reach for this object. And as it pushes these objects, of course, these objects interact with each other, and then the robot needs to have predictions about how these objects move. It needs to make sure that this object goes into the hand, but no other objects, and objects don't fall off the table. So we are interested in problems, planning and control problems of generating such robot motion. And one of the aspects of this problem that we're interested in is, as we are, and that I will talk about in this seminar, is how can we actually represent the physics of such scenes? And we are interested in physics models that can span this spectrum of fine to coarse models. So fine models are detailed models, highly accurate models. Coarse models are lower dimensional models or inaccurate models. And can we span the spectrum during planning and control is one particular topic that we are very interested in, and we just started actually working in this area, and this is the direction that we are currently following. And the second topic, as I mentioned, will be human-robot forceful collaboration. This will be a slightly different focus, and here the focus will be, imagine you want to apply some forceful operation on an object. So there is a board, let's say, and then you want to cut a hole in this board, and as a human, and then you want a robot to help you with that. You want to do this collaboratively. Of course, as you're cutting the board, you will be applying forces on this board, changing forces. And imagine doing it with a friend of yours. The person who will be holding the board will need to hold it for you, will need to change the direction of the board. So there's some collaboration going on. So one of the works that we have done is planning such a collaboration where the robot holds the board to resist the forces that are being applied that may be changing, during the operation, right? Here, for example, the direction of the forces are changing. And so the grasp of the robot may change, but also changing the pose of the object to keep it stable, but also to make the interaction comfortable for the human. And then the robot may need to re-grasp the object as well, change its grasp, and planning that whole operation, this sequence of grasping, ungrasping, re-grasping, and changing the pose of the object. How can we do that is a question that we have been interested in. So these two topics will be particularly my focus, and in the forceful collaboration work, one point I will try to make is that we recently started to take into account the biomechanical model of the human and integrate into the planning of the robot, so that when the robot plans, it doesn't only optimize for its own stability and for its own parameters, but it also plans together jointly for the humans' parameters, particularly to reduce the muscular load of the human. So it's become a joint optimization problem, and that is how the planning goes. And I will present some work about that. But okay, so let's first start with the physics-based manipulation part, the first object manipulation part. And I want to go back to how I started in working on this. This is a video from my PhD, and this is the robot that I worked on during my PhD. And with this robot, what we were doing was, here's a younger version of me, detecting an object using this camera here and the laser scanner here, and then planning and grasping an object. And this has been mostly the primary method of object manipulation, and still is. You detect an object, you estimate its pose in the world, then you make a plan, you move your hand there and close your fingers. And this works most of the time. And the way this works is through grasp planning and motion planning. So grasp planning is about given an object pose, finding a hand pose around the object that gives you a stable grasp. So here the blue mesh is the object, and the black one is the robot, and the red ones are what we call the friction cones. So at the contact points between the fingers and the object, that is the span of forces that can be applied through the frictional contact between the fingers and the object. And basically, you can use this friction cones to analyze whether the robot has a good grasp on the object, a stable grasp on the object, whether the forces within these friction cones can resist particular external forces. And then once you can make such an analysis, you can, given an object pose in a real environment, you can search for different configurations of the hand around the object to find stable grasps for different hand models. You can do that based on where the fingers will lay on the object. And then once you find such a pose, what you traditionally do is motion planning. Let me see. Motion planning. So, and motion planning is usually collision-free motion planning. So wherever the robot arm, hand is starting and you want to reach the pose where you planned for the grasp, and then motion planning basically takes the hand, avoiding the obstacles in the environment that call configuration. And the particular idea that we have is that this can actually fail in quite a different scenes, environments. So here, for example, the same demonstration that we were doing with this robot, and what I had realized was that, so here, for example, again, the camera detects the object, the motion planner plans its motion, the hand goes around where the object is, so it's not too bad, but the object is slightly off, the camera estimated its pose slightly off, so the grasp fails. So what is the problem here?
Why is the camera rotating, Mehmet? I didn't understand that. Why is it rotating?
That's not the camera, that is the laser scanner.
Oh, laser scanner, okay.
Yeah, so here, this thing is the camera.
Yeah. Okay.
This is the laser scanner that's trying to get a 3D point cloud. So the problem here, what's the problem? The problem here is that the camera says the object pose is here, but actually the object pose may be here or here, somewhere around it, but we have some uncertainty about the object's actual pose in the environment. And when you try to just reach for the object directly, you, if you're unlucky, you may hit the object like what we have seen, or you may miss the object. So I was doing my PhD, I was thinking about, okay, how can we address this problem? And mainly my PhD was about building a planner that can reason about the way the object, whether it is at this pose or at this pose or at this pose or at this pose, wherever it is, reasoning about the way they will move when we execute a pushing action. And these are called funneling actions in the literature, such that wherever the object is, it will funnel into the hand, so that we can have a more robust grasping action. And then basically I looked at analyzing what we call capture regions. So we call these push grasps, and for given push grasp, we analyzed what is the region in front of the hand in terms of the object's pose. When the object is cylindrical symmetric, this can be represented as a 2D region, but when it is not cylindrical symmetric, then this region becomes actually three-dimensional region, X, Y, and rotation of the object. And computing these capture regions and then checking to see if the uncertainty coming from the camera is within these capture regions, which will give us robustness as we plan these grasps. Now, that was our attempt to make these, I'm not gonna play again. Why? Okay, so what we realized though is that, let me see if this is horrible. Let me see if any of my feature. All right, can I use another few minutes to try to fix this? I don't know. I can download, because these are talks that are work. I'm now using a
generic video player. I think, like, I forgot the application.
Okay, apologies again about the problems. So we said this was what we had done, and then the thing is, after we looked into pushing to reduce the uncertainty, what we realized was that we could, like, the robot was using pushing not only to reduce the uncertainty into the hand, but it was able to plan grasping actions where here, for example, when it wants to grasp this blue box, normally, if you just do grasp planning and motion planning, it wouldn't be able to put its fingers here because of this object, but it was able to plan actions where it pushes this box first away from this bottle while the box rotates into the hand, so that it was able to execute grasps even under cluttered environments like that. So which gave us ideas about extending the planner to more cluttered environments. So here, this won't work, but a PR2 robot reaching into a fridge to push around obstacles to reach for objects. So what we did was build planners that can work in cluttered environments. But one limitation of my PhD work, and that is where I'm trying to get to, was that these planners, the robot hand was pushing only, they were built such that the robot would push an object, but it wasn't allowed for the object to then contact another object. So the hand could push multiple objects in the same time, but object to object contact was disallowed. And the reason was that because the uncertainty of the physical interaction was basically just exploding. So our robustness estimates were not holding anymore. And this was necessary for us because we were here doing open loop execution, right? We are planning these pushing actions, and then we close the eyes and execute them. So, and these are not possible in realistic environments like this. When you're reaching into a fridge like this, if you're pushing an object, that object will contact other objects. You can't avoid that. So after I came to Leeds, that was what I focused on, making these planners closed loop. so that in such environments they can work while object contact is also there, and work. So we focused on closed loop pushing, and then the approach we took to this was a typical approach of trajectory optimization. So we start with some initial trajectory, and then we would optimize this trajectory based on our goals. For example, the goal object getting into the hand, no object being pushed to the edge of this table. So we optimize a motion like that, and then we would keep doing this optimization as the robot moves, right? So the robot would execute some parts. So it's what we call online view planning. It can also be called model predictive control. So the robot executes part of this plan, and once this plan and then looks at the state of the environment again, and then once it updates its state of the environment, because the objects will move differently than its expectations, it will warm start optimizer and then change the plan, re-optimize the plan, and then will execute the rest, so that it can deal with unexpected motions due to interaction between these cluttering objects. So as I mentioned, this was a trajectory optimization problem where part of the cost was the goal cost, the target object being inside the hand, or the edge cost, where as the objects were pushed to the edge of the table, the optimizer, the robot will be penalized. Well, no, it won't work. Okay, so, and we were able to get this working. So if this video worked, you would see the robot pushing objects around while objects can contact with each other, and the robot reaching for the goal object. But it had certain limitations. So the limitations were that, first of all, this was very slow. Now that we are actually doing re-optimization and replanning as we are moving, this was particularly slow. And this slowness is not only a matter of waiting for the robot to move, but if the planning is slow, it also reduces the dynamic actions that the robot can do, right? If it wants to accelerate objects, then the next time it can update its control becomes a problem. For these optimizers to work, the problem must be locally solvable, otherwise it can get stuck at local minima, because these are local optimizers that we're using. It requires tracking object poses among clutter, and these pictures, we have markers on these objects. These little balls are motion capture markers, and that is how we have been tracking, in this case, all these object poses, which is a problem. And then the control problem must be, so there are other limitations. The control problem must be what we call intrinsically stable. That means if there is a bad contact, it can lead to failure. So the contacts shouldn't do anything unexpected. They're very different from what the robot predicted they will do. And static obstacles are still problematic. So as you have seen, we don't have any boundary of like a shelf environment, because when there's jamming, when we are pushing an object that is jammed, that can actually still lead to very high forces, and they are difficult to deal with. Still, we are doing experiments for that, and we have successful plans that we can execute in such environments with boundaries, static obstacles, but they are still problematic. Now, today I wanted to talk about, but of course, because of the time we have lost, I will try to maybe skip some of these and particularly focus on a couple of those. But I was going to talk about how we have been trying to address particularly these three problems. And to address the slowness issue, as I mentioned at the beginning, we have been looking at using computationally cheaper physics models. To address the second issue, that the problem must be locally solvable, basically the initial trajectory that we start the optimization with must be in a good region so that the optimizer can then find a plan that actually works in the locality of that initial plan. So we have been looking at using human intuition into giving high-level plans to the robot, which can then be optimized by the robot. And then in terms of getting rid of the motion capture markers and doing visual tracking of the objects in clutter, we have been very recently looking at physics-based object pose tracking, combining vision and physics predictions into tracking the objects among clutter. Now, this is mostly video, so if I try to explain this, it won't be meaningful. Oh, but I can play the video because I know where it is. Okay, good. Yeah, I can do that. So let me quickly go over this one. This is the longer one, so I will try to be quicker with this. But basically, this first work has been by with the Magwell, and what we realized is that this planner is slow mainly because of the computational expense of the physics model. So we need to roll out physics simulations as we do this optimization, and they are the key bottleneck. And then we asked ourselves the question, okay, how accurate do we really need these physics predictions to be, right? Because we may be able to trade off accuracy with computational speed. So the physics predictions are basically solving an initial value problem, right? So we have, so X is the state of the environment, U is the control of the robot, F is the system dynamics, so the physics simulation, and X dot is how the state evolves as the robot applies the controls on it. So this is what the physics simulator solves. It integrates this. And then we were interested in, okay, can we do this in a much coarser but faster way? And can we use it during planning? Because we may not need the physics predictions to be very accurate, right? So, and the way I try to explain this is that, so we can integrate this more accurately and computationally more expensive, or computationally cheaper but less accurately as we integrate this. And our predictions will be less accurate about how the state will evolve as we execute these actions. Now, here, there is some useless accuracy. And the important thing is where shall we integrate this, right? Why is there a useless accuracy? Well, first of all, there is the model versus the real world discrepancy. What I mean by that is the simulator is just a model of the real world. It's not the real world. So even if you integrate it very, very accurately, it will actually be different than the real world. So if you know how different it is, actually you can integrate it less accurately, because the more accuracy here is not going to give you anything in the real world, right? So this is, similar to the sim to real gap that deep learning people also talk about. But even in a model-based control framework like this here, we are saying we don't need to integrate the simulator as fine as we can, because the real world won't move like that anyways. But there is more than that, right? So there's also the real world stochasticity. What I mean by that is this is not about the physics engine. This is now about the real world itself. And I don't know if it won't, but there is very good work from Alberto Rodriguez's lab at MIT, where they basically take this object and to the best they can, they push this object in the same way from the same starting position in the real world thousands of times, and they record the object ends up, okay? And they show that it always ends up in a different place. The distribution is actually quite large. This is what we call real world stochasticity. So the real world doesn't always move the same way, as much as we can control and sense it, right? So then again, you don't need to integrate your physics engine more accurately than the real world stochasticity if you have a model of that. But we actually have even more useless accuracy here, which is the task requirements. So not all tasks require integrating the physics model accurately. So for example, imagine these two tasks. And we had a paper on this where we actually developed controllers for this. So these are the same tasks. We are going to push this object on a platform into the green region. the thing is, and without making it fall, the problem is that here the region is very narrow and the goal region is very small. And here the table is quite large and the goal region is quite large. And what we show is that actually the controller, depending on the accuracy required. So here you really need your physics predictions to be accurate, both to keep the object on the strip here and to hit the goal region. Here you can actually afford to have inaccurate physics predictions, because if you have a model of your inaccuracy, you can predict it won't fall off the table anyways. And when you aim for the center of this goal region, even if it ends up far because your predictions are inaccurate, that's still fine because your goal region is large. So what we show here is that actually here the robot slows down and the physics predictions take a much longer time. Here it is much faster because it actually can afford to be fast and it doesn't care about accuracy. So this is what I mean by the task requirements. So we have been interested in building such models and using them in planners. So ideally what we wanted was we have a hierarchy of physics models, not a single F, which is what is usually used in planners today, but a hierarchy of physics models, where at the bottom we have the very fine model. This might be, for example, your physics simulator integrated at a very small step. This is accurate but expensive. And at the high levels of this hierarchy, there are very coarse models that are less accurate but cheaper. And one question is how to generate such a spectrum of models, obviously. And I won't go into the details now, but like we have actually used a parallelized scheme where you have one coarse integrator and one fine integrator. The fine integrator here can be, for example, your physics engine. A coarse integrator can be a model that you have learned, a coarse model, which is something that we use. We learn the coarse model and then we use the physics engine and we combine them. Basically, the coarse model, which is cheap computationally, you run it in on the single core for the full duration of the prediction. And then you use those initial states and you run the fine physics engine, which is computationally expensive, on parallel cores. So the red lines here represent starting from the initial predictions of the coarse model and running the fine model in parallel. And then you basically have a sweep with the coarse model again in the second iteration to update the trajectory again on the single core. And then you use the starting model, starting point again to run fine, and you can keep doing this. And basically, if the number of iterations that you have here is less than the slices that you have, the cores that you have, you save time. And basically, we have shown that we can. So this is the error that we have. This is applied to pushing a box. This is the error we have compared to integrating this pushing action very, very finely. So the ground truth, when we have different iterations of this algorithm on the horizontal axis here. So 0, 1, 2, 3, 4 are the iterations of this algorithm. So at 0, it is the basic coarse model we have. At 4 iterations, we basically go to the fine physics model, the physics engine. But in between, we show that actually we do reduce the error at log scale, so exponentially, and with different iterations, and they correspond to paying much less computational time for integrating these models and using these within planners. And we have also applied learning the coarse model here and applying this to multiple objects physics as well. So yeah, Wisdom has worked on this work. He did a great PhD. He recently graduated, and then he actually is now at currently at UC Berkeley. We have recently applied this to multi-object planning, but this will and submitted this to ICRA. I wanted to show it to you. I can. I wonder if I should spend time. No, let me go because let me go forward because I don't think we have time. to find the video in the files and everything. So the second topic I wanted to talk about today was human in the loop planning. And this is work by Rafael Papalas, who was also a PhD student with me and now a postdoc working with me. And as I mentioned, the trajectory optimization methods we have are locally optimal. So they can actually get stuck at local minima. So in this video, for example, the robot tries to get to the green object, but this object gets into the hand before the green object, and the robot is not able to escape from that local minimum. But what you would have seen is the human, we have a human interface. Basically, human goes, are you able to see my pointer? Yes, okay. The human goes and basically clicks on an object and a position to move the object to, and that is all the human does. And then that is integrated into the optimizer. And then the robot easily finds a solution. So we have been interested in this work, how to, so it looks like this. The human goes and clicks on object, clicks on a position, and then that is used within the trajectory optimizer so that the robot can actually go and then the robot optimizes the rest of the plan, but it actually helps the robot a lot because then it's not stuck in that local minimum. So, and we have looked into different ways to integrate this optimization, the human input, human suggestions into trajectory optimization. We first did a study where it was part of the initial trajectory. Then we also looked at using the human inputs as additional cost terms in the objective function, not only at the initial trajectory, but the human could provide inputs as the robot was planning, and they can then be integrated into the objective function. Instead of, so at the beginning when we did this, we were again interested in the human providing the inputs at the beginning as part of the initial trajectory, but then we realized that actually some problems the robot is able to solve by itself if the problem is easy. Then we don't want to spend the human's time. We don't want the human time is valuable, so we don't want to spend human's time. So we said, okay, we can actually request the human input only if the optimizer is stuck at a local minima, right? So we developed, we changed the planner to do that, and we evaluated that method because the vision that we had was that, so let's say you have a warehouse and you have robots working in different shelves, but you have only one user, one human supervising these robots. And the human is in front of a computer and the scene is shown to the human just says, oh, okay, move this object to this position, and then that should make your task easier to the robot. And then the robot just takes that and plans, and maybe another robot with a problem then is shown to the user. So that was the vision that we had. So we wanted to minimize the time the humans spend for each robot, because that means that then we can have a much bigger warehouse with many more robots that one human can control. And that is why we looked into robots asking the human input only if they get stuck at local minima. We have worked with that, and these were some publications that we made at ICRA and RAL in 2020 with that. But then recently we extended this. We realized that actually we can then do better than asking the human for input when we get stuck at local minima, right? So then we asked ourselves, okay, when to ask for human guidance? We can ask when planning gets stuck, like we did in our studies published in 2020, or we can preemptively predict whether the human guidance will be useful in a given scene, right? If the robot can predict that it will get stuck, then it can ask the human for input, because then it doesn't waste that planning time and see that it actually gets stuck, right? So I will call this non-predictive. This actually asks for human input when it gets stuck, the optimizer. This one tries to predict whether the human input will be useful for a given scene, and then asks for input for that. And we basically done that recently and has shown that. So the blue one is the predictive one, and the orange one is the non-predictive one here. Shown that for 10, even 20 robots, the time that the robots take for planning is actually reduced in a statistically significant manner when we use the predictive approach. And the success rate also is increased when we use the predictive approach. And the prediction here is basically coming from a neural network. So we feed in a representation of the state, and then we predict a optimized trajectory cost, and we train this neural network. And then when the robot has a new state, it runs it through the neural network to predict how much optimization, how much cost reduction it will be able to achieve in that particular scene. So the robot is trying to predict if it will get stuck or not. Now, of course, you might think that, okay, if the predicted cost is high, if the robot knows that it will get stuck, it should ask for human help. That was our first attempt. But then we realized that actually that is not the correct thing to do, because the problem may be so difficult that even the human input may not be very useful, right? So what you want is not just the prediction of how the robot optimizer without human input will perform, but also how the human will perform. So we want to predict whether the human input will be useful. So what we actually look at is the gain from the human input. We predict the gain from the human guidance, which is basically the predicted trajectory cost with autonomous planning. So we have two of these neural networks. One of them predicts the trajectory cost with autonomous planning. The second one predicts the cost if there was human guidance. And then we look at the difference between the two. If there is significant difference, if the predicted cost with the human guidance is significantly lower, then that is when we go and ask the human for input, because that means that is a scene where the human will create a difference. So this was how we integrated the human in the loop in these planning scenarios, and we're interested in this one human guiding multiple robot scenarios in the warehouse. This one is of course not going to work. This is a recent, so this is about tracking objects as we manipulate them and getting rid of the motion capture markers. If I have time at the end, maybe I can show this video to you, finding it in the folders. But yeah, so this is basically about our recent work about physics-based object manipulation. And we have a big project which started in last December and is going to go for 5 years until the end of 26. That is about warehouse picking and packing with physical reasoning. So our goal there is to build a system which can do a top-down manipulation in a box where, for example, this robot wants to reach this object with the star. We want to build these systems that can push these objects out of the way and grasp an object, or similarly do the packing task of the robot nudging these objects out of the way to insert an object in a packing scenario. So that is the vision we have, and that is something that we are working towards. Okay, so that was physics-based. So I know I'm out of time. Very quickly, let me show you these. Oh, now this decided to work. No, it won't. It didn't. Okay. So during my postdoc, I actually worked on multi-robot collaboration. So here the robots were planning to grasp an object and move it to assemble a structure. Here, how the robots grasp, how the robots move, that was all the output of my planner. And then once I moved to Leeds, I was interested in doing this in a scenario where the other side was a human, as I showed at the very beginning. And part of this problem is planning the grasps. So as the human is applying forces, the robot needs to find the grasps that will resist these forces, right? Here, for example, the human is applying upward and leftward of the human forces. So the robot comes up with these grasps that will resist those forces. But as the human keeps cutting, some of these forces will go downward. So the robot needs to lift this gripper and put it here so that it's able to resist the downward forces. And as the human then starts to go to the right, then it needs to lift this gripper and grab here to resist the rightward forces. And it needs to plan, of course, we don't tell it to do this. The robot needs to plan all this by itself and perform the regrasping operations, right? Because otherwise, if there are forces that are not resisted, then these are some failure examples. Slip can occur if there's too high torque around the grippers can rotate. They may not be able to resist those forces. So the robot needs to be able to plan the grasps that will resist such forces. The other problem is regrasping itself. So when the robot lifts this finger here, if the object is heavy, it may actually sag like here. So it may not be able. So regrasping is not an easy operation. So actually part of this planner is making sure the object is stable during regrasping. So the robot, for example, first tilts the object like this so that the object will not sag like this when this gripper is released, and then goes and grasps here and then brings it down. And if the video later works, I will show you an example of that. But this was basically a multi-level, multi-modal planner where we would first plan the grasps on the object that will resist the forces. So here, for example, these grasps will resist the forces shown in black, and then these grasps will resist the one in the red, and these will grasp the remaining ones. And then these will give us a sequence of grasps, which we would try to connect by regrasps, and then we would do the motion planning. So this was a sequential multi-level planner like that. Yeah, I won't go into details of this, but this is how we check about the stability of these grasps against the applied forces as the human applies forces. And yeah, it won't work. Okay, and but then, as I mentioned, what we realized was that here until here there's no human in there. What we realized was that actually it was quite difficult. If we fixed the object pose, it was quite difficult for the human to perform all these operations. The human had to go into very strange pose configurations to perform the operation. Therefore, we looked into integrating human models into the planner. And we looked at two tasks. One is puncturing task, where the human actually just pushes into a thick foam board to create a hole. And also cutting task, where the human, for example, starts from here and cuts and until the end here. And I know I'm out of time. I will finish in 1 minute. So here the input to our planner is the starting pose of the human, the pose of the robot, and then a task where there is a force to be applied on the object. It might be the puncturing force or the cutting force at a point on the object, and the mass of the tool as well, and the grasp of the human on the tool. And then the output of the planner is a robot configuration and a configuration of the object, so a grasp and a robot configuration that will keep the object stable when the forces are applied, but also minimize the predicted human muscle activity. Okay, now the predicted human muscle activity depends on the predicted human configuration, right? So the robot may put the object at a certain pose, but how the human will shape his or her body is not something the robot can control. And the muscle activation depends on how the human will shape their body. So here you can make the planner to minimize the predicted muscular activity for a distribution of possible human body shapes, or you can assume that the human is intelligent enough to pick the body shape that will minimize the human muscle activity. So you can pick the object pose that will minimize the muscle activity assuming that the human will be able to pick the correct configuration for themselves. Or you can try to minimize the worst that the human can do. So there were all these different, and we tried different versions of this, but the best version was actually the humans were quite good at finding the correct pose for themselves. So we were able to optimize the object pose according to that. And we actually did some studies with EMG readings to verify if we were able to minimize these human muscle forces. So we had our planner here hold the object, that is the comfort planner. The baselines we compared against was a random planner. So the robot would pick a random pose and the human would apply the operation. And then we had a user-defined pose. The user-defined pose was, so with the Baxter robot, you can actually hold the robot's hands at the cuffs and then move it. So the user was free to move the robot and the object at a pose that they think were comfortable. And we compared all of them using EMG readings in terms of how much muscle activation they resulted in. And we did this at the top, we show it for the puncturing task, and here at the bottom, we show it for the cutting task. We did it for both tasks. With cutting the results, so here we show the blue one. So here at the horizontal axis is this measured muscle activity using the EMG readings, and at the vertical axis is the force that the human has been applying, which we were also able to measure using a force torque sensor on the robot. And so lower left corner is better here. So because that corresponds to lower muscle activity and lower force applied by the human. Basically the blue region is our planner. The red region is the user defined poses, and the gray one is the random planner. And for cutting, our results were not very conclusive. And we think that is particularly because, as you see, the blue region is good, not bad, but there's lots of overlap between these regions. The reason we think is cutting is actually, so our model was assuming a single point of force application, but cutting was actually applied over a long cutting line. And therefore our model was not exactly representing what was happening in the muscular forces. We think that's one explanation we can come up with. But for puncturing, the results were actually much better. And that is the thing, because the puncturing is actually applied at a single point. And that is a better representation of our model. Here, as you can see, the random planner is clearly doing worse. And the user-defined red planner is doing okay. It has a good overlap, but the comfort planner is actually able to be better than the others, especially the randomized pose. So some open questions that we still have in this is how to do this for dynamic tasks. As I mentioned, we only do this for a single force point applied. As I mentioned, this is one of the reasons we think why cutting has failed. And how to plan for the continuous forceful interaction between the human and the robot. So combining the human muscle optimization with the motion of the robot is something that we still need to do. Until now, we have only done either the robot's motion without human optimization or the human optimization with a static pose, but we want to bring these two together. And these are the people, my students, postdocs, and also collaborators who worked on this. Okay, so apologies about the delay and all the technical problems. But I also had a reklamlar section. So if anyone, there are any master students, undergrads interested in a PhD or postdoc, I want to say, please feel free to contact me. I don't have any immediate openings, but I expect to have some at some point in the future soon. So I'm happy to discuss such opportunities with anyone interested. Good, thank you, and apologies again.
All right, thank you, Mehmet, for your presentation, and I'm sorry about the video issues.
No, I'm sorry.
I
As
hope
I
that we
mentioned,
can resolve them eventually.
yeah.
Maybe we can take some questions. Like
Yes.
I know that students may have some classes, but 1 or 2 questions.
Yes, of course. I understand people may have left.
Uh,
Let me also, while I take the questions, I will try to find one of the videos that I wanted to show.
One quick question I have, like, so you mentioned about this fine coarse physics-based models, but nowadays people talk about this GPU-based computing, NVIDIA cards, and things like that. So I'm trying to understand better. Like, isn't that possible to do those simulations, physics-based simulations, using like parallel computing, graphics, GPU-based systems in real time, especially the problems that you're working seems to be solvable with those kind of features.
So there are simulators that are running on GPUs, but they do not necessarily have a method to trade off computational expense with accuracy. That mechanism doesn't exist. So what we have tried to do with this method is that we want to be able to say, this is the amount of accuracy I need for this task. Give me a simulation, give me a prediction that is only accurate up to this accuracy. So make it as cheap as possible, right? So that kind of a method doesn't really exist, and that is what we have been trying to do. Now, our method also does parallelization. We only did CPU core parallelization until now. GPU parallelization is something that we want to do because it can actually do the time reduction even more. But otherwise, yeah, because the way traditionally physics engines work is that they do numerical integration, right? This is either Euler integration that you take step forward, or higher order Runge-Kutta integration method. So basically, this is initial value from numerical integration, and these whether they work on the GPU or CPU or all of the current physics engines basically do a forward integration. What we try to do is to be able to do this integration where we can suggest the accuracy that we get from that integration, basically. Yeah. So the answer is no. Like, you can't really do that with any existing simulator.
Any other questions while
Maybe I can ask a short question. So Mehmet, about those that work you did about pushing objects, you assume you have access to the full state of the environment, right? But from the first person perspective of the robot, maybe like this might be like a partially observable environment, but still from the movement of the objects, maybe the robot itself can somehow build a rough but more complete picture of the world state. Are there any such work?
Yes, actually, you're right, and we did some work like that. So let me try to share my screen. Are you able to see this?
Yes.
So this is some work. I didn't talk about this, but so this is some work like you're talking about. So here, what we have is the robot is searching for an object, but it's not visible. And on the top right here, what you see is the robot also has a model of the occlusions, what it is not able to see. And here, this work where we combine planning with reinforcement learning, and the planner, it doesn't only generate the robot motions, but it also learns about where the hidden object may be. You will see it as green object appearing here as the planner works. Now I'm running it. So you will see this in top right, the robot planning and also having hypothesis about where the green object may be. And the basic also running a forward planner. What you see, those quick motions there are to predict how the objects in the environment will move, and as the robot moves and plans. So yeah, I agree. I mean, we are aware that this is going to be a partially observable problem, of course, and we will need to address this challenge, especially when we are reaching into these bins from top down, right? And related to this, a recent work that we just submitted to ICRA is also, kind of related to what you asked, where we use physics to also predict the object pose. So, for example, so here's a oops, sorry. Here's a cluttered environment where, I mean, it's not the exact same thing, but we are pushing the single object, but there are other objects. So here you will see two wireframes overlaid. The green one is our method, and the yellow one is DOP. I don't know if you know DOP, but it is deep object pose estimation. So it is given the camera image, this camera image, it actually estimates the object pose. The problem is that, as you said, when there are occlusions, when you don't see objects, you can't predict their poses. But what we do here is we combine the visual input with the fixed predictions, because we know the robot controls that are executed, right? So we can actually use that information as well. So what you'll see is that as the object becomes invisible, the yellow wireframe will go crazy because it's not able to see it anymore. But the green one, we are still able to make consistent predictions about how the object is moving, because we are actually also using the physics information behind the scenes, right? And now this requires you to at least have an idea about where the object is at the beginning. So if you have never seen the object, you can't do this. But if you see some of the objects, then actually as you are physically manipulating them, even if you don't see them in later time steps, you can still track them, right? So these are the different, and we want to apply this. We submitted to ICRA just last month, and we do want to do this. This is just an example where we show that if the object is visible, then actually both of them do quite well. Still, the vision-based, since it's independent from the previous time step, it can sometimes flicker, but it is quite good. But we start to be much better when there is actually occlusions and the object is not visible completely to the camera. So these are the kind of directions that we're exploring in this direction. Does that answer?
Yeah, really cool.
Any other questions? Maybe we can close the session. Like I know that students have other things and the faculty has maybe some other meetings. Mehmet, thank you for your presentation, and
thank you very much. And apologies again about the problems. Yeah, apologies.
It's happening.
But thank you. It was fun.
Thank you for joining us and giving us a nice presentation. Thank you.